Right. So good morning all of you. The summary of the last lecture, we have discussed this lattice vibrations, density of states. Right. Actually, what we find is density of lattice points, not a density of vibrations. Density of lattice points. So, we got 1 dimension, 2 dimension, 3 dimension. Actually, we have done for two purposes. First one is audio is okay? Right. So, what we have done is, we have find the density of lattice points as well as the density of states. The density of states will be used for the free electron theory of metals. Maybe tomorrow we will start that. Fermi energy, all those things we will discuss. Very, very crucial. And here what we are using today is density of lattice points. But we want density of vibrations, lattice vibrations. But each lattice point is associated with how many oscillations? 3 oscillations. Am I right? Along x, y and z. That's why the density of lattice vibrations is nothing but 3 into density of lattice points. Is that clear? But here, how many lattice points are there? Let us say n. So that's why the whole lattice, what is the density of modes of vibrations? 3n. 3n into density of, that's good. I hope you understand. Good. Now take a fresh page and put the heading specific heats of solids. Specific heat of solids. Maximum you will get questions from free electron theory of metals. Very, 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 very crucial. Till now, all years one question is there. That means whatever the number of years you have CSIR exam, every time you have one question in free electron theory. But this is also very important. Ready. So specific heats of solids. Okay, we are talking about the specific heats. That's why we have to go to the first law of thermodynamics. So let us go to first law of thermodynamics, and this is a thermodynamic system, let us suppose, and here I am giving some heat energy, let us say delta Q. Whatever the heat energy given to a thermodynamic system, that is utilized in 2 ways. One is to perform work, another is to increase its internal energy. That's good. Whatever the heat energy given, it will raise the internal energy as well as it performs some work. The first law of thermodynamics is nothing but the law of conservation of energy. That's why whatever the amount of energy given, that is equal to dq equal to delta u plus delta w. Okay, so I can write like this, dq equal to du plus dw. Everybody know what is a dw? pdv. Now let us talk about the specific heats. How many types of specific heats are there? 2. Specific heat at constant pressure, specific heat at constant volume. First let us see. The specific heat at constant pressure is nothing but dou q by dou t at a constant pressure. At least some of you know, have the idea of thermodynamics relations. And similarly, specific heat at constant volume, dou q by dou t at a constant volume. Very few people are responding. That means you didn't study intermediate. Cp dou q by dou t at constant pressure, Cv dou q by dou t at a constant volume. Once again, at constant volume. So just now you have seen dou q is nothing but dou u plus dou w. What is this? Constant. If volume is constant, could you please tell me what is the dV? Volume constant dV. Zero. If dV 0, dW equal to 0. That's why the specific heats of solids at a constant volume is always equal to dou u by dou t at a constant volume. Specific heats of, specific heat at constant pressure is how much? Dou q by dou t. Shall I ask a question? Generally, which is more, Cp more or Cv more? How do you know? dou q equal to dou u plus dou w, but here only dou u. Here one extra term is there, am I right? So generally for gases always Cp is greater than Cv. I hope you know the Mayer's relation, Cp minus Cv equal to R. That is for gases. We are not studying anything for gases. What we are studying? Solids. But unfortunately for solids, you have taken this solid, okay, you have given some heat energy. Then according to first law of thermodynamics, some internal energy is increased as well as some work is performed on that. Whenever work is performed on any thermodynamic system, either volume will be decreased or volume will be increased. Work done by the system, volume increased. Work done on the system, volume decreased. Anyhow, once work is done, there is some change in the volume. Will you observe that change in the volume in this solid when you are giving some heat energy? Say yes or no. Will you identify? Why? In case of solids, the change in the volume is very, 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 very small. I hope everybody understand. For solids, that change in the volume, work is performed, no doubt, but that change in the volume is very, very small. That is very small. That's why you can take dV is nearly equal to 0. If dV equal to nearly 0, then your for solids your dQ is nearly equal to what? That's why your Cp equal to whatever you have written, dou Q by dou T at constant pressure, whatever Cv you have written, dou U by dou T at constant. For solids, Cp is nearly equal to Cv. So for solids, specific heat at constant pressure, specific heat at constant volume, both are nearly same. The reason is, in case of solids, we won't identify that much significant change in the volume. That's why dV you can neglect it. That's why dQ is nearly equal to du. This is for solids. So what you studied in intermediate, Cp minus Cv, all these things are for gases. But solids, it is both are nearly same. Am I understand? Good. That's nice. Now come to the, so finally what you are finding is a specific heat at a constant volume. What is the formula? Good. So finally we got Cv equal to dou U by dou T at a constant volume. You are finding Cv of what? Lattice? Say yes or no? That means you have to find the internal energy of what? Lattice. Once you got the internal energy of lattice, simply differentiation with respect to time, and this is nothing but the Cv. Differentiation of the internal energy with respect to temperature. Sorry. So finally what do you want? U lattice. U lattice. U lattice is always equal to U, lattice vibrations or 1 minute, yeah. Lattice vibrations. You can say this instead of lattice, we can say solid. This is better. You are finding the Cv for what? Solids. Yeah, lattice okay, but better word is a solid. Yeah. So internal energy of a solid is nothing but what? Internal energy due to lattice vibrations plus internal energy due to free electrons. Internal energy due to free electrons. This is the thermal excitation of the electrons. That is, we'll start tomorrow. This is a very, 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 very important concept. Thermal excitation of electrons. But for the time being, we are in the lattice vibrations. That's why we are neglecting this. Say yes or no? Neglecting. While I am explaining, deriving everything, I told you, we are neglecting that free electron contribution. So finally, we have to find this lattice vibrations. So that means internal energy we have to find. That is your internal energy due to lattice vibration. This is our task. Okay, come on, start. Total 3 theories are there. First one, Dulong-Petit. Dulong-Petit. And the next one, Einstein. And the next one, Debye. Spelling check ma. These are the 3 models we are going to discuss. In all those 3 models, for every model what you have to find is U, internal energy due to lattice vibrations. Both the specific heats for solids are nearly same. The reason is there won't be there is no significant change in the volume whenever you are giving some heat energy. Now let us start the discussion with the Dulong-Petit law, that is a classical theory, and the remaining 2 are quantum, and this one is a classical theory. Ready? Right. Now let us see the first one, Dulong-Petit law. This is the classical model. So everyone please listen. Okay, so here we have an atom, for example. Okay, so this is having 3 modes of vibrations, that is along x-axis and y-axis as well as z-axis. Okay, x, y, okay, whatever it is, x, y and z. I would like to write the Hamiltonian because it's a classical one. Hamiltonian means not quantum one. Hamiltonian, classical Hamiltonian. Okay, right, ready. So I hope everybody know what is the potential energy. The potential energy is nothing but a half, summation over I xi square, because half k x square plus y square plus z square, 3 degree of freedom. Okay, so I would like to write the Hamiltonian of the system. The Hamiltonian H is equal to kinetic energy, summation over I pi square by 2m plus summation over I half k xi square, where I is running from 1 to 3 and here also 1 to 3. So this is called how many coordinates of P? How many coordinates of X? This is called 6, what is that? 6 dimension. 6 dimension of what? Phase space. Because 3 position coordinates and 3 momentum coordinates, total 6. Dimension means how many coordinates you are taking. Okay, in real space 3D we will say, why? 3 coordinates. In phase space 3 position, 3 momentum, total 6. That's why the dimension of the phase space is 6. Good. Now here I have to introduce one theorem called equipartition theorem. Equipartition theorem. Derivation is in the StatMech. Just I am giving the statement here. I will derive in the statistical mechanics. Equipartition theorem. So what is this equipartition theorem? Are you ready? Each quadratic term contributes half kBT to the energy of the system. Okay, right, ready. Each quadratic term of Hamiltonian contribute half kBT energy. How much? Half kBT energy. According to this, how many quadratics are there? 3 here, 3 here, total. That's why it is 6 dimension. Is it okay? Right. So each quadratic contributes half kBT. But how many quadratics are there? That's why this is what? 6 into of kBT. How much? 3 kBT. But there is no one atom, because here you have taken only one atom. But how many atoms are there? N atoms. Like this, how many atoms? That means you have to write the Hamiltonian for how many? N atoms. So finally, it's a scalar quantity. No need to worry about that. For a total solid equal to N into 3 kBT. So how much? What is N kB? What is N kB? Only when N is Avogadro number. If N is Na, then only it is R. Otherwise no. Okay, but generally order we will take Avogadro number, then we will write R. If it is simply N, we should not write R. Okay, careful. If this N is Na, what is Na? Avogadro number. Then it is 3 Na kBT. Then this is Na kB is nothing but, that's good. So finally, U solid equal to how much? Now once you got U solid, CV equal to how much? So if you take the graph for classical model, this is the temperature and this is the CV, and for all the temperatures how much you got? For lower temperature also T, for higher temperature is also T. But what they experimentally found, experimental data, from the experiment, what is the data we collected? First point, at high temperatures, the CV is equal to 3R. CV equal to, oh, that means your Dulong-Petit law is valid for high temperature. Good. Second one, at low temperatures, that too, as a T tending to 0, the CV is also tending to 0. But which law? T cube law. Obeys T cube law experimentally. So CV at low temperatures obeys T cube law. Don't forget amma, set question. Obeys. Next, third one. So here we have non-metals. Yeah, solids means non-metals are there or not? Sometimes we have metals, and sometimes we have what is this? What is that? Layered solid, layered ante 2D, layered spelling, layered solids. Next, sometimes we have linear chain lattice, something like this. So what they observed experimentally, if it is a non-metal, the specific heat equal to alpha T cube. For non-metals, the specific heat is CV equal to, for metals, CV equal to alpha T cube plus gamma T. Some people will write AT cube plus BT also. Is it okay? Good. CV equal to? Alpha T cube plus gamma T. Alpha means what? Linear expansion coefficient. Gamma is what? Volume expansion coefficient. Beta is what? Surface or areal expansion coefficient. In intermediate you studied. Okay, no problem. So layered, CV equal to alpha T square, 2D. I hope now you can guess. It is a 1D. CV equal to. So this is the experimental data they confirmed. So but unfortunately our Dulong-Petit law is satisfying only at a high temperature. That's why you have to search for something else. Okay, come on. Linear is enough. This one? Okay. Please check when I am writing on the second board, are you getting any voice disturbance? Is getting low or high? Second board, please observe. If anything is, please tell me. Did you observe anything to now? No? Okay. Because the receiver is this side, I am little bit far away, that's what I am checking. So the classical theory fails at low temperatures. For metals, only one term, alpha T cube. For non-metals, for non-metals one term. For metals, alpha TQ plus gamma T. That was your gate question also, CV for metals. So, what is equipartition theorem? So, each quadratic term contributes half kB. I want to ask you something question. Ready? Take ideal gas. Ideal gas is a 3 dimension. Good. Potential energy, what is the potential energy of ideal gas? Inta doubt. Ideal gas means no interaction. Potential energy is 0. So, this term won't be there. Whatever may be the potential energy, it is neglected. So, what it will be there? Kinetic energy. What is the, summation over I? Pi square by 2m. So, how many p squares are there? 3. Px square, py square, pz square. Now, tell me, for ideal gas, what is the energy, average energy? Half kBt into 3. 3 by 2 kBt. N atoms, 3 by 2 n kBt. That is a benefit of this equipartition theorem. We can find the average energy. Ready? Over. Stop. The next one, Einstein theory of specific heats. Listen please, stop writing, please listen. Actually, what this Einstein considered, a classical oscillator is replaced with a quantum oscillator, that's it. He treated that Dulong-Petit law is a classical oscillator. In the place of classical oscillator, he has taken quantum oscillator. So everybody know quantum oscillator energy E equal to n plus a half into h cross omega, where n equal to 0, 1, 2, 3, so on. Wait a minute. Okay, first let us see what are the assumptions he made. He made some assumptions. First one, all atoms are identical. All atoms are identical, just like a Breve lattice, identical. Next, second one, the motion of atoms is independent of, independent motion. Motion of atoms R is not for atoms. R is for what? 64 marks. Motion of atom is independent of other atoms. Independent of other atoms. This is the wrong assumption Mr. Einstein assumed. He considered the motion of the atoms are independent of each other. That's the problem. What is the problem? That finally you will understand. Just underline that. Okay, and one more thing. Listen. Now here I have taken an atom. This is one atom. Each atom is having oscillations along x-axis, along y-axis, and along z-axis. That's why if you consider one atom is equivalent to 3 quantum oscillators, 3 quantum harmonic oscillators. Cool. But here the lattice contains what? How many atoms? N atoms. So lattice or solid, whatever it is, how many atoms? N atoms. That's why N atoms are identically equal to how many oscillators? 3N oscillators, of course quantum oscillators. So what I am going to do is, once again, we have to find average energy of all those N atoms. Say yes or no? But that N atoms are equivalent to 2. Now I am going to find the average energy of one oscillator by using quantum mechanics. After that I will multiply with what? Is it clear? Ready. So let us find average energy of one oscillator. Everyone please listen, I have taken one oscillator of mass m or something k, and whose energy E equal to n plus a half h cross omega. I have given a function f of x. Can you please tell me what is its average? Integral f of x dx by integral dx. Integral dx. F of t I have given. Integral f of t dt by integral dt. Say yes or no? Wait. Now I am coming out of this solid state physics. Whenever you want to find any average, Babu listen please. Average of f of x. The definition is very simple. F of x average equal to integral f of x dx by integral dx. Whenever you are using integration means what? Continuous system or continuous energies, continuous function, whatever it is. Is it a classical or quantum? ఇది ఉంపలేగా. కంటిన్యూస్ అంటే క్లాసికల్, ఇంటిగ్రేషన్ అంటే క్లాసికల్. ఓహో, క్వాంటమ్ అని హెడ్డింగ్ పెట్టాడు కాబట్టి ఇది ఏదైనా క్వాంటమ్. వెరీ గుడ్ అమ్మా. ఇంటిగ్రేషన్, ఇంటిగ్రేషన్ మీన్స్ వాట్? కంటిన్యూస్. లిజన్ ప్లీజ్. కంటిన్యూస్, కంటిన్యూస్ means classical or quantum? Good. Continuous values exist for classical system, but I want for quantum system. Very simple. Integration is replaced with summation. Is it okay? So that's it. And integration is replaced with the summation. So we will write it as f of x. At dx I can't write here. Okay. What is the reason? Some variable here it will come. Okay, I can't write. Okay, just remember integration is replaced with summation, because dx means integration over what variable? What variable? X. So summation over that variable will come. And then summation f of x dx you can't write. Understand? Yes, wait. Okay, fine. Now what do you want? Average. Now let me write average energy classically. Classically. First let me write classically. Are you observing? Still if you are not understanding this, it will come in the statistical mechanics. No need to worry. Everything we will derive each and every average energy. Partition function, average energy, ideal gas, classical system, quantum system, everything. But meanwhile you have to remember this. Now classical. Integral. What you are finding? Energy. That's why your function is what? E. Into e raised to minus beta e. dE by integral e raised to minus beta e dE. Just remember for the time being, what you have written in the denominator is the partition function. What is that? Partition function. Just remember. But this is the definition of average energy. This also will derive, no need to worry, but here I can't derive. Good. Now I am writing the quantum. Are you ready? Integration is replaced with summation. Energy. Energy, come on, I say. Okay, okay, say. E raised to minus beta I. Nothing will be there. Divided by summation e raised to. Super. Up to this everybody understand? Maybe you don't know how we got this, but I will explain in the statistical mechanics, no need to worry. But if you want to get quantum, integration is replaced with summation. That's it. 1 second. Finally, you got U equal to summation energy e raised to minus beta e by summation e raised to minus beta e. Maybe you are getting a doubt. In summation over what, sir? In the energy, what is the variable, sir? N. That is the summation over n. Carefully see. Carefully see. I will ask a question. Over? Write this expression in terms of differentiation. I want differentiation of something that is equal to that one. I want differentiation of something and which is equal to this one. What differentiation? Differentiation with respect to E. Anybody? Beta. Sure. Pakka. Say. Next, anyone? Correct? Sit down. Dou by dou beta of, okay, so this is the log of summation e raised to minus beta e. You please differentiate this. 1 by summation e raised to minus beta e into summation e raised to minus beta e into minus beta minus e minus e. So that means what is missing here? Understand? Once again, this is the average energy formula we got. I would like to write in the differentiation form. So that is dou by dou beta of log of f of x. Dou by dou beta of log of f of x is what? 1 by f of x into f dash of x. Again you will get back this. But one minus is missing, that's why I have written minus. Is it clear? If anybody still not understanding, I have used this dou by dou x of log f of x equal to 1 by f of x into f dash of x. This is the technique I have used. Good, very good, Babu. Now this is the energy. Okay. Ready? So you know the summation runs from where to where? 0 to infinity. Forget about logarithm and all these things. Just to focus on this. Please focus on this. Are you ready? Right. This is nothing but summation e raised to minus beta n plus a half h cross. I am taking only this term, Babu. Summation e raised to minus beta h cross omega by 2. I am splitting that. E raised to minus beta n h cross omega, where n equal to where? Are you observing? Which is nothing but, this is a constant outside. Baba, I am taking only this term. I am not taking any other, only concentrate on this. E raised to minus beta h cross omega by 2. Ready? Now put n equal to 0. 1. Plus, put n equal to 1. Put n equal to 2. So this is nothing but e raised to minus beta h cross omega by 2. This is the, what is this? A geometric progression. Infinite terms are there. This is the sum of infinity terms. Sum of infinity terms is equal to, what is A? What is R? Still I am saying I have taken only this summation. Okay. So I hope everybody got it. Can you please write this in the numerator, and can you bring this term to the denominator? How much it is? 1 by, okay, first write. This is only this summation, not a total. Be careful. I am taking this summation. So e raised to minus beta h cross omega by 2 summation e raised to minus beta n h cross omega, where n equal to 0 to infinity. And this implies e raised to minus beta h cross omega by 2. This is the geometric progression. If you put n equal to 0, 1 plus e raised to minus beta h cross omega plus e raised to minus 2 beta h cross omega plus so on. This is the sum of infinity terms, a by 1 minus r. If you write that, you will get e raised to minus beta h cross omega by 2 by 1 minus e raised to minus beta h cross omega. Only that summation term. Einstein assumption is independent oscillations. Finally, I got u equal to minus dou by dou beta log of that summation entire thing become e raised to minus beta h cross omega by 2 by 1 minus e raised to minus beta h cross omega. Now, I request you split that logarithm and differentiate it. Log a by b equal to log a minus log a minus log b. Take this summation and substitute here, then the split the log a by b, and after that differentiate. If you didn't understand, please wait. Just apply log a by b, log a minus log b. So, first term please observe log of e power something, log of e power something, first term. Is it completed? Ma, first board is, anyone is writing? Please take this term, summation term, and keep it here and apply log a by b, log a minus log b. First term, log of e raised to minus something, log of exponential something is always a something. Ready? Right. So, if anybody is still not understanding, minus dou by dou beta, this is what I am saying is log of e raised to minus beta h cross omega by 2 minus log of 1 minus e raised to minus beta h cross omega. Now I request you, this is nothing but minus dou by dou beta log of exponential something is a something by 2 minus, this is as usual, log of 1 minus e raised to minus beta h cross omega. I request you do the differentiation, minus minus cancel, differentiation with respect to beta. How much first term? H cross omega by 2. Next, dou by dou beta of log of f of x, 1 by f of x into f dash of x. Careful, minus minus 2 times you will get. In the numerator 2 minus will come. Careful. 1 for this, 1 for this. Do it, do it. How much? E raised to beta h cross omega by 1 minus e raised to minus beta h cross omega into right, h cross omega by 2 plus, I think here you got 1 by 1 minus e raised to minus beta h cross omega into minus e raised to minus beta h cross omega into minus h cross omega. That is why, please check your answer, h cross omega by 2, this is the average energy for one oscillator, plus h cross omega e raised to minus beta h cross omega by 1 minus e raised to minus beta h cross omega. Everybody got this? Bring this e raised to minus beta h cross omega to denominator. Now write for solid. If you want to write for solid, you have to multiply with what? 3n. That is for entire solid. First you find for one oscillator, I have already explained, one solid contains n atoms and one atom is equivalent to 3 oscillators, the total 3n oscillators. Because it is a scalar quantity, just add, that means 3n times. So in every derivation what you are finding is internal energy or average energy of the solid. In this Einstein model we got 3n h cross omega by 2 plus h cross omega by e raised to beta h cross omega minus 1. All of you got this? Come on, differentiate. 1 minute. With respect to T, with respect to water. Ready? 1 minute. So this is the U given. What do you want? CV. Could you please tell me? CV equal to how much? Dou U by dou T. 1 minute, 1 minute. But there is a beta. 1 by kBt, yeah? Okay. So, this is nothing but beta is nothing but 1 by kBt. Shall I write directly here? Okay, I will do one thing. Here I will write beta equal to 1 by kBt. Okay? So, that's why I can write this step directly here. Careful, Amma, carefully do the differentiation. So, this is h cross omega by kBt. Everybody written kB? Have you written k? I will throw the notebook. kB. kB for? Hero. My favorite hero. Come on. Now differentiate with respect to temperature. Human beings are incarnates of God. That means he is nothing but God. First term 0 because it's a constant. 1 by f of x differentiation minus 1 by f of x whole square into f dash of x. Be serious. You have to pay tribute to those people by learning the subject. That is the great tribute which we can pay to those people. So, I think you got first term 0 and after that minus, okay, because by e raised to h cross omega by kBt minus 1 whole square into f dash of x e raised to h cross omega by kBt into minus h cross omega by kBt square. Huh? 3. Printing press corrections over. At the end of the coaching also, if you are not doing the differentiation, your 50,000 loss. Ready. So, this minus of course, okay, leave it. Now, everyone stop and see the board. CV equal to, stop writing and see the board. Amma, here h cross omega, here h cross omega whole square, here kBt square. Oh, I can't write kBt whole square. I want to write kBt whole square. So, 3n is there. That's why I am multiplying with the kb here. Then, luckily, h cross omega by kBt whole square into, so here I have something e raised to h cross omega by kBt by e raised to h cross omega by kBt minus 1 whole square. Up to this, any trouble? Right. Many times in the quantum mechanics also, I told you sometimes exponential function is a constant, exponential function is a constant, something like that. Exponential wave function is always a even function. The reason is what? It's a constant. Now please observe that exponential power what you are having. H cross omega by kBt. Now carefully observe, very important. The same discussion we will do for Debye model also. That's why listen carefully. Here theta E, there theta D. E for Einstein, D for Debye. So H cross omega by kBt. So here I am assuming this quantity. H cross omega by kb. So here we are assuming H cross omega by kb as theta E. Einstein characteristic temperature. Einstein character temperature kaada. Einstein characteristic temperature of the solid. Einstein characteristic temperature of the solid. E for Einstein. So that's why theta E by T. Theta E by T. Okay na? Now CV become 3n kb theta E by T whole square e raised to theta E by T by e raised to theta E by T minus 1. Super bumper. This is the specific heats of solids according to Einstein theory. Now we have to check at a high temperature what, at a low temperature what. Are you ready? Now I am checking at high temperature because this is easy. At high temperature. Ready? Am I important? So first, wait. So we are taking two cases at high temperature. At high temperature, everyone please listen. What is the meaning of at high temperature? Theta E by T, temperature is very high. That's why theta E by higher value is very much less than 1 or less than 1. Whenever x is very much less than 1, could you please tell me e power x is nearly equal to how much? 1 plus. Now everyone see, CV equal to, come on say, 3n kb. Are you observing? This is what? Theta E by T whole square into, what is this e raised to theta E by T? 1 plus theta E by T by 1 plus theta E by T minus 1. That's why 1 gets again theta E by T. I hope everybody understand. That's why these two gets again theta E by T is very much less than, but you are adding to 1. That's why again this is neglected. So finally CV equal to 3n k 3n kb. If n is Avogadro number, how much? 3r. So at high temperature we got CV equal to how much? Next one, see, very interesting. So I don't know space is sufficient or not. Ready? So this is very crucial. At low temperature. At low temperature means theta E by T is very much greater than 1. So theta E by T is very much greater than 1. Ready? Ready. So theta E by T is very much greater than 1. Then what to do? So CV equal to, are you observing? Come on, 3n kb theta E by T whole square, careful, into. This is very much greater than 1. Then exponential theta E by T is also very much greater than 1. Shall I neglect this one? E raised to theta E by T whole square, E raised to theta E by T, both are Cancel. Then finally what you get? Say yes or no? Now, specific heats of solids at low temperature according to Einstein's are 3 n k b theta e square, everything is a constant. That's why I am taking constant by t square. Are you observing? Come on. E raised to minus theta e t by. Understand? Shall I ask? Ready? Once again. At low temperature, what is the specific heat you got according to Einstein model? Some constant. As t tends to 0. As t tends to 0. Sorry, at low temperature. As t tends to 0. Cv tends to. Ready? Listen, that's why this is crucial. If you observe carefully, the specific heat according to Einstein model, my interview also they will ask. It is a proportional to e raised to minus theta e by t by t square. So Einstein model is having two relations, and a specific heat is having two relations. One is exponential law, another is 1 by t square law. In your exam, you will get this question. According to Einstein model, at high temperature, at a low temperature, the specific heats of solid obeys A, exponential law, T cube law, 1 by T square law. What is your answer? Why? Exponential function rapidly changes over any algebraic function. T square is an algebraic function. Exponential function always rapidly change compared to algebraic. Here two functions are there. One is exponential, another is algebraic. But exponential function rapidly changes. Please write clearly. Exponential function rapidly changes with respect or compared to algebraic function. That's why if anybody asks in the exam or interviews, the CV law, which law it is? Exponential law. Not 1 by t square law. Einstein law is exponentially decreasing. Whatever it is, exponential, some negative is there, exponentially decreasing. That's why as a t tends to 0, that is also tending to 0. Is that clear? That's it. Please write clearly there. Why you are neglecting t square? Exponential function rapidly changes over, or exponential function is dominant than algebraic function. Algebraic. Or exponential function rapidly changes over algebraic function. Any word you can use. and tomorrow's class is very crucial. But before coming to tomorrow's class, I request you please go through the density of states and remember those expressions. Come to the class. Density of states, please don't neglect. Ready? So, have we written there properly? That is, exponential function is dominant over algebraic function. That means it rapidly changes over algebraic. That is why if anybody asks Einstein law, at Einstein theory satisfies which law? Exponential law, not 1 by t square law, it is exponential law, right. Next. So, the third one, last and final, put the heading, take a fresh page, Debye model. Take a fresh page. Debye model. Ma spelling D-E-B-Y-E. Okay. Debye model. Oh, Debye. Bye. Debye model. Write down. Assumptions. Here Debye model simply one word, solid, as a system of, in the heading you please write, a system of coupled oscillators. This is the difference between Einstein model and a Debye model. So they will ask in interviews, what is the difference? Einstein taken independent oscillations and a Debye considered coupled oscillations. Write down. Assumptions. Vibrational motion of, first point, vibrational motion of the crystal, the vibrational motion of the crystal as a whole, the vibrational motion of a crystal as a whole is considered as the vibrational motion of a system of coupled oscillators. a system of coupled oscillators, a system of coupled oscillators, comma, which can propagates, oscillate means what? There is some frequency range, which can propagate a range of frequencies, which can propagates a range of frequencies from 10 to the power of 4 hertz to 10 to the power of 12 hertz, from 10 to the power of 4 hertz to 10 to the power of 12 hertz. Have you heard this frequency range anywhere? Write that in bracket phonon spectrum, in bracket phonon spectrum. Next point, total number of, no, sorry. Next point, the motion of such a solid, the motion of such a system, the motion of such a system can be described, the motion of such a system can be described in terms of normal modes of vibrations, in terms of normal modes of vibrations, full stop. Next point, my important, put a star mark. Total number of normal modes of vibrations, total number of normal modes of vibrations of solid equal to 3n. Einstein taken 3n oscillators, and here lattice vibrations, density of lattice vibrations we will find, and after that we will find the total lattice vibrations, those equal to how much? 3n. So ready. Stop. So here we have one lattice point. Babu, listen please. Stop writing. At least each lattice point we have an atom. So you know that atom is having 3 oscillations along x and y and z. Einstein taken independent oscillators whose energy range is from 0 to infinity. But Debye considered those are coupled oscillations within a frequency range. That is most important. Okay. Now here we have one lattice point, but actually how many lattice points will be there? N lattice points, let us suppose, or n atoms, whatever it is. Are you listening? Now here the point is, we want to find density of normal modes, density of normal modes of vibrations of solid or lattice. This is what we have to find. Is it clear? But what he is saying is that the density of normal modes of vibrations of solid is equal to how much he said? Total 3n. Here we are not talking about total, just we are talking about what? Density of solid. Ready? Each atom contains how many vibrations? 3. Like that, how many are there? That's why total is what? 3n. Equal to 3n, wait a minute, into, yesterday we find something, density of lattice points. Because each point is associated with one atom. That atom is having vibrations. Are you understanding? How many vibrations? That's why density of normal modes of vibrations of solid is nothing but 3n into density of lattice points. Density of the point. Because each lattice point is associated with one atom. Each atom is having 3 vibrations or 3 oscillations. That's why this entire solid is equal to 3n into density of. Is that clear? One second. Okay, I am taking only one atom, that is why what is this 3 into n. Finally, if I take while you are integrating, you have to equate it to 3n. Ready. So, only one atom I have taken, that is why 3 into density of lattice points. Ready, Bob? All of you. Up to the vibrations of atom. Okay? Huh? All right, ready. So, in the last class, we have already got this density of lattice points. Everyone, please listen. Density of lattice points. If you want to find the density of lattice points, first you have to find n, number of lattice points. Number of lattice points. I hope you remember the volume 4/3 pi k cube by volume pi by L whole cube. But out of this valid R, that's it. I think you got V for L cube by 6 pi square k cube. I hope you remember. అందుకనే that's why better to see the notebooks. Yesterday you have derived, check. P by 6 pi square. Please check once. మీ బొంద 4 2s are 2 3s are 6 కదా. Ready. So now here we are finding a dn. Dn is equal to how much? V by 6 pi square 3 k square dk. So yes or no? This is nothing but V by 2 pi square k square dk. Now 1 minute. So we know velocity equal to omega by k equal to omega by k, dk equal to, now that implies dn equal to v by 2 pi square k square omega square by v square dk d omega by v. Finally, dn by d omega equal to v by 2 pi square omega square by v cube. This is what I told you, please remember, please remember. So dn by d omega, this is the number of lattice points. I repeat, these are the number of lattice points. dn by d omega equal to, and density of lattice points or number of lattice points within the frequency range omega to omega plus d omega. Ready. dn by d omega equal to v by 2 pi square omega square by v cube. Okay. Right. So I don't want in terms of omega, I want in terms of nu. That's why omega equal to 2 pi nu. Can you please convert this into nu? Come on. Equal to 2 pi d nu. Take this and substitute. Do it. And finally tell me what is dn by d nu. Not angular frequency, we will write in terms of frequency. That is lattice, density of normal modes of vibrations of lattice, but total when you find, then it is equal to 3n. It's a lattice only, not atom. Lattice equal to 3 into density of lattice points. Please cancel and finally get the answer in terms of nu, dn by d nu. How much you have to get? 4 pi v nu square d nu by v cube you have to get. 4 pi, 4 pi capital V, 4 pi capital V nu square d nu by v cube. Write nu and v separate as differently. Don't write it as quite similar. So, we are trying to show that experimentally Debye model is satisfying that experimental results. At low temperatures obeying a T cube law, at high temperatures it is a constant. So, here we have some restriction with the Debye model. I can't derive completely. The reason is we need the distribution function of phonons. Distribution function of phonons is a bosons. Bosons distribution function is 1 by e raised to alpha plus beta e minus 1. That you don't know all these things. That is why we have some restriction. So, but don't worry, we will try our level best. Where we will discuss distribution functions? StatMech, photons, phonons, fermions, everything will come. Maxwell-Boltzmann statistics, Fermi-Dirac and Bose-Einstein statistics. So, before discussing SSP, SM paper should be completed. If your SSP sir is explaining all those things, you won't listen. But your SM sir is explaining all those things, you listen. More Fermi statistics, Bose statistics. But here, SSP, solids. Why this fermions related, distribution function related? Up to what you can understand, we will derive, and from where the StatMech will come, there we will stop and we will take the direct expression. Once the statistical mechanics is completed, we will leave one half page and again we will derive this, okay, after that distribution functions. Okay, I must see the final expression. You got 4 pi v nu square d nu by v cube. Stop. So once again, what is this? Dn by d nu. How much you got? 4 pi v nu square d nu by ఏంటమ్మా again d nu by v cube. Stop. Okay, so this is what the density of lattice points. I repeat, these are the density of lattice points, but each lattice point is having 3 modes of vibrations. That's why this you have to multiply with what? 3. Wait a minute. Dn by d nu, the lattice. Okay, so then what is this? You have to multiply with 3. So 3 multiply, how much it is? 12. You have to multiply with 3. Come on, say 4 pi v by v cube into nu square. All of you please listen. Okay, so here what I am doing is 4 pi v as it is and nu square also as it is, but I am writing here 3 by velocity cube v cube. Are you observing? Careful. Sir, what is this dn by d nu? These are the number of modes of vibrations. Here I am not talking about number of lattice points. Actually what you have written is the density of lattice points, but each lattice point is having 3 modes of vibration. That's why now the number of modes of vibrations, because already multiplied with 3, number of modes of vibration, modes of normal, number of normal modes, modes of vibration. Wait a minute. Number of modes of vibrations in the frequency range. Listen, very important. And in the frequency range, nu to nu plus d nu, because you have taken d nu. And this is a notation. This is having a special notation. G nu d nu. That is the density of states representation. G nu d nu, G k d k, G omega d omega, G of v dv, G of e de, all are same. All are same. Just remember G nu. Okay, 1 second. Finally, we got G nu d nu. What is the meaning of this? Number of modes of vibrations in the frequency range. Okay na? If I say number of modes of vibrations in the energy range, then G of E dE. In the velocity range, G of V dV. Okay, good. Equal to how much? 4 pi V nu square 3 by V cube. Wait a minute. This 3 by V cube, 3 modes of vibrations. How many? 3 modes. Out of these 3, 1 is longitudinal, 2 are transverse. That's why this expression can be split into 1 by VL cube plus 2 by VT cube. That means out of those 3, 1 longitudinal mode and 2 transverse mode. Which one contributes, all those things are different, but those are the normal modes of lattice exist actually, 1 longitudinal and 2 transverse. So finally we got G nu d nu equal to 4 pi V into 1 by VL cube plus 2 by Vt cube into nu square. Wait a minute. Now I want to find total modes of vibrations. Total modes of vibrations. These are the modes of vibrations only in the frequency range. You want total integration. Okay. Hello, here also d nu missing something d nu missing, or this is defined as a d nu, g of nu, something d nu is missing. 4 pi v 1 by vl cube plus 2 by vt cube into integral nu square d nu. Must be there, d nu must be there. That means these are the modes of vibrations in the frequency range in nu to nu plus dv. Yes. Only dn. First I have written d nu there only, na? Then we have to remove this now. This is the number in the frequency range which is defined as g nu d nu. That's proper. That's right. Now ready. So 4 pi v 1 by vl cube plus 2 by vt cube, and I told you it is not taking up to infinity. So there is some range. That's why this frequency range is from 0 to nu d. D for Debye, which is maximum frequency available. So then finally, in the assumptions he said the total modes of vibrations is equal to how much? 3n equal to 4 pi v into this one as it is 1 by vl cube plus 2 by vt cube into nu d cube by. So from this what you are going to find is what is the maximum Debye frequency, which is equal to 9n by 4 pi v into 1 by vl cube plus 2 by vt cube whole power minus. So this is the maximum possible Debye frequency in the lattice vibrations nu d cube. Up to this only we can derive. After this we can't do. Without Bose-Einstein statistics we can't proceed. But a direct expression we will take, and we will show that at low temperatures how it is varying at high temperatures. But still, after the total discussion, please leave one side page, and once the statistical mechanics Bose-Einstein statistics completed, then again we will come back and we will solve this. Okay, first item. It's not dn by, it's simply dn, sorry, because this is the number in the range. Although you are not understanding, but don't worry, but better to remember this, because if you are writing a set exam, you will get this maximum frequency available. That is the Debye frequency, maximum frequency. Now onwards it is related to the boson distribution, that means the Bose-Einstein statistics. Phonons are bosons, you know that. We can't handle now. Once Bose-Einstein statistics are over, again we will come back to this. Although I explain, it won't be, it won't fulfill. you will get bored. Now if I explain. So why you have multiplied with the 3 means we have taken lattice points, but each point is having 3 modes of vibrations along x and y, z, something like that. That's why we multiplied with the 3. And from here to here, why you got 3n means this is the total modes of vibrations. According to Debye, this total is always equal to 3n. So we have to show that at low temperature satisfying T cube law, at high temperatures it is a constant. In Bose-Einstein statistics we will use one integral. Anybody knows what is that integral called? Riemann-Zeta integral. Okay, no problem. If SM is completed, you will have that idea, otherwise how you will know? I am taking this final expression U solid, but this is not, I am not deriving this. I need not to say what is a theta d here. I told you earlier theta E, theta d. This is Debye model, that's why theta d, nothing else. Right, ready. So now please focus on this. This is what I am saying. Actually we want to derive this. For that we have to take integral E bar f of E dE, where f of E is what? Distribution function. But we don't have any idea of distribution functions right now. That's why we are skipping that derivation part, and finally we will come to this. Again I promise you, after this please leave one page half side. Half side is enough. I mean one side is enough. One side is enough, and after distribution functions in StatMac again we'll come back to this. Ready? Come to the result, because without knowing why to discuss all those things, a time waste. Now I am taking at low temperatures. Okay, first one is what? High temperature. So at high temperatures, okay, so what is X? How to give that? X equal to h nu by kBT. H nu by kBT. Ready? Right. At high temperature, am I ready? So you have taken here x equal to h nu by kBT. As the temperature is very high, then x is that means very much less than 1. If this is very much less than 1, then e raised to x is nearly equal to how much? If I write 1 plus x minus 1, 1 gets cancelled. What is the remaining? X. And the numerator? X cube and x. Are you interested? Now u equal to 9 kb T T by theta d whole cube. Now integral as it is. Now this is x cube, this is x, finally x square dx. From where to where? Theta, that is a maximum, okay. So 9 kbt T by theta d whole cube. So this is nothing but x cube by 3, theta d by t whole cube into 1 by 3. So how many times? 3 times. These two gets cancel. 3 n kbt. This is a solid. Cv equal to dou u by dou t. How much? If this n is Avogadro number, Cv equal to 3r. Any trouble? No. Next come to this. Ready? So here this is at low temperature. So at low temperature, that means what? X is very much greater than 1. And we can't do any approximations here. Everyone please listen. This is u equal to 9n kbt T by theta d whole cube integral x cube by e raised to x minus 1 dx. From where to where? Theta d by t is tending to. T is tending to. That means this is tending to. Okay. The low temperatures tending to 0. That means that is values are tending to infinity. This integral is called Riemann-Zeta integral. What is this value? No, we can't solve this. It's a standards value, pi power 4 by 15. Let me check once. Yeah, pi power 4 by 15. Now take it. U equal to 9 n kbt t cube by theta d cube pi power 4 by 15. Now take everything constant. Some constant into t cube. T power. That's it. Everything remaining, everything is constant now. Understand? This is what? Now Cv equal to dou u by dou t. This is a proportional to what? So at a low temperatures, your Cv is a proportional to T cube. So which law it is a satisfying? T cube law. And if you draw the diagram, this is a T and this is a Cv. So exactly it's a satisfying T cube law, and here it is a 3r and it is a proportional to how much? T cube. That's it. Only you don't know how you got this and the rest of the things. This also I don't know how many of you know about this word, Riemann-Zeta integrals, and this value is a standard integral values, pi power 4 by 15. Again you will get this integral in two ways, two places. One is Bose-Einstein condensation. Another is again Fermi energy changes with respect to temperature. There also you will get. Write this, after that leave, no problem. Continue. Continue, amma. No problem. After that again next page we will derive this. What is the problem? After writing this, one side leave, Babu. And tomorrow we are going to start the most important contribution, that is a free electron contribution. So here we have already shown that it is proportional to T cube, and one more contribution is there, that is a free electron contribution. What is the free electron contribution? Proportional to T. So some people will ask, which contribution is more, lattice vibration contribution or free electron contribution? Lattice vibration contribution is more. Write continuation and leave half side. We can derive that expression back side. What is the problem? మరి స్కూల్ పిల్లలాగా బిహేవ్ చేస్తున్నాయి. Initially I thought that complete that integration also, but after that I thought it will become another language movie with subtitles, so better to wait for some more time.